This week, we're going to look at what is known as an RLC circuit. And let's see, we've looked at capacitors, we looked at resistors and capacitors together. Now we're going to look a little bit more in depth at the combination of these three things. So when we draw the schematic for a capacitor, you guys have already seen this capacitor schematic and what it looks like. It kind of looks like a battery, but the battery has the long side and a short side for negative and positive. But just remember that a capacity is a way of storing electrical charge, right? So like your battery on your phone has a capacitor built into it. And its units are in farads. And I think we were using millifarads last week, right? But in any case, standard unit is in farads. So if you get millifarads or megafarads, use the appropriate conversion factor so that it's in SI units. So this week, the new item, it's not really new because we looked at it last week, but I don't think we gave it a specific name, is the inductor. And so remember what we did last week, we took a wire and we spun it around. I went through sort of a caption, a cartoon, an animation, where we started off with a wire, a straight wire. We sent a current through the wire, and depending on which way the current was going, told us which way that field was going. So if the current was going up, the field was going kind of in and out the board using our right hand rule. And so then we expanded on that. We said we're going to take that coil or that wire and we wrap it around a few times and we make a coil. And from that coil, we get even more more of a magnetic field. Again, refer back to that animation. I'll put it in the notes of this at a later point. So you'll see that in an email, just in case. So animation. Okay, so what an inductor does, as by its name, it induces a magnetic field, it creates a magnetic field, and it stores that energy. But this time, as opposed to the capacitor, which stores it in an electrical field, let's write that down as well. Units are in henries. Okay. So all of these different items have their own kind of unique units associated with them, depending on who discovered it, right? And so in a scenario such as this, one thing that you're going to need to know for an inductor, even though it induces a magnetic field, it hates a change in current. It wants to push that current away. And you'll see in a second how it's going to want to push some current, and the change in current, it's going to want to push that away. Okay, so we're going to also talk about something called resonant frequency, and we'll get a little bit more into that. But by way of a mathematical process, we need to know how to calculate it. And the resonance frequency is found by taking 1 over the square root of the, remember that's the inductance, which are in henries, over multiplied by the capacitance, which are in farads. Okay, so I did a quick calculation there, and so our frequency in this case would be 1.141, and this is in radians per second. Right? And remember, radians are a unitless dimension, but I'll write it in here. You can write it either way. So this is that number. You're going to want to probably keep that number in mind because it's going to come up later on in a different sense. But I'm not going to tell you, so this comes by way of your calculations today. Okay. So in our experiment today, we're going to be asked, and I'll walk you through it. See if I can move this over a little bit more so you can get a better view. So we're going to be asked to put an inductor, a resistor, and a capacitor in series with one another. We're going to try and put all three of these things in series initially. Now, the new piece or the new characteristic that we're going to look at now comes by way of an alternating current or an AC circuit. So we're kind of moving from a DC circuit where we have a battery and it has sort of a direct constant current to an alternate current. So this is our symbol for an AC current. So it's going to pump it out sort of sinusoidally, and you'll see it, and it'll look sort of like a sine or a cosine curve or graph. And remember, it has some frequency, and so the frequency we're gonna measure in hertz here, and there's a relationship between this frequency. Maybe I should call this F, because this is the way it's written in your book. So in the simulation, F is going to be your frequency in hertz. And remember what a hertz are basically the number of cycles per second. All right. So those are hertz. Well, I'll show you what a hertz looks like and how to calculate it on a graphing calculator in a minute. Okay, so we have some current going through here. It's going to go through the resistor. It's going to go through the inductor. It's going to go through the capacitor, and it's going to kind of oscillate in a sense. Okay. And again, you'll see it. Okay, so one calculation that you're going to need to know is you're going to want to be able to figure out the voltage root mean square. And what a root mean square is, it's our equivalent voltage to our DC voltage in a sense. All right. So when we create a DC circuit, we're going to want to know a lot of times how much power is we want to pump out. So if we have a lamp or a light bulb, we want a certain wattage to go to that light bulb. So obviously it's as bright as we need it to be. And so our voltage root mean square is the equivalent calculation in an AC sense. All right, so just think of it as an equivalent calculation to the voltage for a DC circuit. All right, and we're gonna try and figure out the relationship between those two. Okay, and I went through a calculation here. So each one of these components has their own root mean squared associated with it in an AC system. And these numbers I'm going to pick off from the simulation. This one I just used Ohm's law on. So the maximum voltage is what we need as a starting point, and we're going to figure out its root mean square by way of a specific formula that you'll see over here, and it's in your handout as well. Now, in AC circuits, we have to talk verbiage a little bit differently. So in an AC circuit, as opposed to in a DC circuit, we're not going to talk about resistance per se. We're going to talk about something called impedance. So Z is considered as our impedance. So I'm not going to get into the process of figuring out impedance by way of how we got to this point, but just understand that there is a real number part. Let's see if I can write that down. So this is the real number part. And this is the imaginary number part. It's not imaginary in the sense that, well, we just dreamed it up. It's imaginary in the sense that it's the complex number. And we can write standard numbers in a complex way. So just remember, go back to you remember the complex form of a number. We usually write as A plus BI, where this part is the real number and this is the imaginary part, right? So just kind of lean back on that experience that you had. You don't need to get too deep into it. You're just going to need to be able to pick off certain values related to the impedance. Okay, so again, our thought now in terms of how we calculate the impedance is kind of similar. Most of the areas are similar to that of resistance. Right? So when we're in an AC circuit, we talk impedance. When we're in a DC circuit, we talk resistance, so that we can kind of communicate here. Now, you'll start to hear some terms that are involved with impedance. So one of them is going to be reactance. So there is a reactance in the capacitor and the inductor. So the capacitor and the inductor we're going to try and find its impedance. There may be some resistance associated with that, but the impedance is what we're going to be looking for later on. So just kind of think of reactance again as a part of our impedance term here. And we're going to come back to that shift over there. Okay. So here are my impedance values. Okay. So this is just a recap of what I just talked about. So the impedance component is a resistance plus some reactance. If we have a resistor in an AC circuit, it could just be said that its resistance is the same as its impedance, and the units here are still in ohms, right? So a resistor in an AC circuit has an impedance, and the impedance still is measured in ohms. Right? The impedance on a capacitor, all of these, by the way, are measured in ohms. It's found by going through this process, and we're going to pick off, mainly we're going to pick off this piece right here. Okay, so omega is the frequency and C is the capacitance. So this is going to be the impedance of a capacitor. Probably should have wrote that here. So this is the impedance of the capacitor. You see that by that C that's there. This one is going to be the impedance of an inductor. So we're going to use that formula. So you've probably seen this formula here for power dissipation. So the power dissipation is going to be found either by taking the square root of the current times the resistance, or the impedance in some situations. And it's also going to be equal to the current times the voltage.
Wait, did you say I squared times the resistance or sometimes the impedance?
Yeah, we'll use this also, but instead we're going to actually, you're going to see it look like, I believe you'll see that.
Okay, thank you.
Okay.
And is I squared like, you meant like a curly line at the bottom, like a wavy line? Is that supposed to represent another symbol, or is it still just I?
Where?
Like I squared Z right there. So the I looks like like wavy. Is that like a different?
No.
Okay, it's just I squared Z. All right, thank you.
Yeah, it's just current. So it's I squared Z. Similar to this, right? Except we're in an AC system. Okay, so to figure out and to talk about frequency, as you guys have already seen in the past, it is measured in hertz. And so if I wanted to figure out the frequency of a system, I'm just basically counting how many cycles I go through in some given time. So let's just say that this is 1 second through this span here. I pick off 2 periods, or I see 2 periods here, or I see 2 cycles. And in this case, the frequency is 2 oscillations per second, or in this case, 2 hertz. If we wanted to write it using omega, just keep in mind that through each cycle, you're going to go through, in most cases of a standard period, sine or cosine, it's going to take you through 2 pi radians. And so in this case, we go through 4 pi radians each second. Okay. So, and this number right here has some value to it that you're going to want to pay attention to as well. Right. Okay. Oh, and this one is in radians per second. So let me share my screen here with you. And while I switch over, does anybody have any questions? Okay, so you should be seeing my screen with my calculator in my hand right there. So we're going to see a couple graphs that you may want to emulate on your calculator to see if your values are in line with what you're getting. So let's just say that we wanted to look at one of these 2 graphs, a sine or a sine graph shifted. So let me turn one of them off. So just kind of be careful here when you graph. You want to make sure you're in the right mode. And so right now, if I hit the mode button, you can see now that I am in radians. And so anything that it's going to calculate is going to calculate in terms of radians. So let me show you the easiest way of at least looking at a few cycles here. So I'm going to set my my window. Oops, let me get into the graph mode. So I'm in the graph mode, and I'm going to set my window such that the numbers are going to be in line with what I want. So let's just say I just made a mistake here, and I put negative 90 to 90 maybe. And maybe I'm thinking, okay, the calculator is going to graph something for me in degrees. Well, if I were to graph that, remember, I think I have it set in radians, yeah. So what the calculator is thinking for this graph that I have highlighted is it's going to give me all the values between negative 90 and 90 radians. So let's see, I'll just do a zoom standard graph. Okay. And let's see what happened to the window. Well, actually, the window changed on me there. Let me do that one more time because that's not what I really wanted to show you. So let's just do a regular graph here. If you looked real closely, it's just drawing a bunch of sine waves between negative 90 and 90 radians. So the window is set between negative 90 and 90 radians. So that's a bunch of periods in there. That's probably roughly about 15 periods on both sides. So if you make that mistake and you're not sure, just use the keystroke zoom and then zoom trig. So the number 7. And so what it does, it'll adjust it so that at least you see 1 or 2 periods in there. Okay. So I'm using a TI 83. You can you should, if you don't have a graphing calculator, there's a bunch of them online. I even believe TI has their own downloadable calculator. But there's a bunch of them that all do the same thing. So here's a sine graph. Most of you guys should be familiar with that. So let's just say I wanted to look at the graph from a standpoint of shifting the graph over. I want to instead move that that graph such that instead of it looking like this, I want to simply move that graph over to the right or to the left. Now, this plus sign here is going to cause, couldn't see that one. All right, that was my graph that I was drawing. So this plus sign here is going to cause a shift to the left so many units. But remember, I need to be in radians. So instead of shifting so many units to the left, 90 radians, I'm going to change that to pi over 2. Right? And so that we can see it a little bit better, I'm going to bump up the height. So I'm just going to double it. Remember, that's just the amplitude. So instead of going between 1 and negative 1, maybe, it's going to go from, it's going to kind of oscillate between negative 2 and 2. But you're going to see the shift. And you're going to also see what I asked it to do is draw it a little bit different. So I'm going to ask it to do it boldface. So let's go ahead and graph that. Okay. So you can see a couple of things. You can see that there is a shift to the left. So if you calculate from that point to that point, you want to kind of match up corresponding points. You should see that that distance right in there, if I'm in radians, should be pi over 2. Right? and the equivalent value for pi over 2 is roughly about 1.57. So let's just verify that. So I'm just going to hit trace real quick. It's going to trace along this axis here. And let's see, I'm going to get point to corresponding point. So I'm on the lighter line here. And I'll pick off this point, which is a root. Actually, I want to look over here. It doesn't matter, but it's just a little easier to see. I'm going to look at this bottom part right here. And so that number is 4.71. And I'm going to compare it to this part over here, which we say is the lagging piece. And so I got to jump off of this one. I think we just hit the up arrow. Yep. We hit the up arrow. I'm on the other graph. And so now I move down here. And now that one is at 3.14. So 3.14 minus, or 4.17 minus the 3.14 is about 5.7. Right? And this is radians, which is equivalent to 90 degrees for our purposes. Right? So there's a shift to the left of 90 degrees. And so so in this case, we'll just say the bold graph lags pi over 2 radians behind the non-bold graph, if you will. Okay. So this one right here lags behind it. So just get point to corresponding point. Okay. All right. So let's look at the simulation. While I'm switching over, does anybody have any questions again? Oh, and I can write on this too, I think. Yeah. All right. Let's exit out of there. And just go back. Keep this out of face. So let's go to our document. You should see the document under course content. I would download the document. Because there are some pieces that don't translate over. So let me just go ahead and share my screen one more time. Share screen 2. Okay. So you should see this document. Okay, so let's go to look at this first piece here. See if I can put these side by side. All right, and so what we're going to be doing is we're going to be putting together batteries and capacitors and inductors. So I'm not going to go through it all because I want you guys to play around with it. But here I have an inductor. You can see what its value is. Its inductance, 3.2 henries. Or you can just simply click on values to see. You're going to probably want to put this in the conventional mode where the current flows in the red here. But you can see what's interesting about this is that the current is oscillating here. There's no AC voltage source. It is just simply oscillating by way of this inductor. So I'll let you think about why it does that. even though this one right here just says just put a battery and a capacitor on there, you're gonna need to work through and get to this point. So I won't give away everything. You're gonna also, it's gonna also ask you to put a current chart on this. You can kind of see, let's see if I blow this up a little bit. You can kind of see how this oscillates. The current oscillates between -2 and +2. That negative just implies that the direction that it's going in. So you can get a good feel for what's going on there. And then what I ask you to do is to create another circuit. Let me drag that over for you. And actually, we need to build that one because the one I was looking at was a little more complex. So let's open up another. Let's copy this URL and open up another. Okay. So let's look at the second part of this circuit setup, where we're going to have a resistor, that's R, an inductor L, and a capacitor C. And we're going to create a circuit with an AC source. So we're going to grab the AC voltage piece. We're going to grab a resistor. So we'll just grab that one. There's another resistor in here. I think it's another lab that has a lot more resistance, but this is enough for us. We're gonna grab an inductor. Remember, it's just a coil wrapped around either itself, or there may be some dielectric in there, maybe a metal piece. If you open up some circuitry and maybe at your house, there may be some dielectric in there. I know, like when I open up my some of my battery operated components, like some clippers that I use, they have that coil in there, so it can store that magnetic charge. And let's see what else we wanted. We want a capacitor, and the capacitor is here. And so we want all of these to be in series with one another. Now, I didn't get around to playing a lot with that multi-sim simulation that you guys played around with last week. So if you feel inclined to do so, feel free to work with that. You should get the same numbers. I just thought that one was a little bit somewhat complex. There's probably too many bells and whistles there, but I think it had some good points to it. So we'll connect all these with a wire. We're in series, remember? And if you wanted to, you could even put an ammeter in here. Remember, the ammeter needs to be in series with this. But we should be able to see the current. We'll put it up there in conventional mode. Right now, it looks like it's pumping out some current, but we didn't complete the circuit yet. So let's complete the circuit. Make it look nice. So you can see here that the AC source is pumping out with some voltage between 9 and -9 volts, right? And what we can also do is we can put a voltage chart and we can figure out what's going on. So it's going to ask you to put this voltage chart on either side of the inductor and the capacitor. I'm just doing it right now on the AC source, and you can kind of see how this is changing between -10 and 10 volts. You can grab another piece or another meter to show what's going on. This is another voltage meter. Just needs to touch somehow. So I won't give it all away, but you can kind of see, let's see. I'm going to pause it right there. You can see now the voltages here are in sync with one another, right? So they're in line. Now, you're going to see later on when we grab, I guess we can only grab 2 of the voltmeters, but I'm going to move it over here, put it across the capacitor and run it. You're going to see that the waves are not in sync with one another. So they are, let's see, so when this one is peaking here, and we can kind of increase this to make them look similar, you can see that one of them is lagging behind the other. Right? So kind of use this as your reference point maybe. So when this one is high, this one is still low. So it looks like this one is peaking behind the other. So the voltage for, which one is this? The voltage across the AC source is looks like it's lagging behind the voltage across this this capacitor. Right? But you're going to be asked to do it across the inductor and across the capacitor as well, and I believe across the resistor. Okay. These numbers are going to be fairly straightforward to plug in here. Just remember, you should be able to calculate the frequency by looking at the chart. It's going to have you figure out what the period here is. You can see that a period can be measured from low point to low point. Right? There's multiple ways of figuring out the period. So you can see here, you would just want to count the squares, get kind of close to it. Each one of these squares corresponds to 1 second. So 1, 2, maybe 2.5 is the period for this wave. Right? So you should be able to, once you figure out the period, you should be able to figure out the frequency. And I'll leave that one up to you, how to find the frequency. These values, which correspond to the impedance of the resistor, the impedance of the capacitor, and the impedance of the inductor, can be found also by looking at the various values across these pieces. There's a calculation piece that you're going to need to go through, and I'll go to that handout in just a second. So we talked about the root mean squared earlier. Again, you don't need to figure out how to get the how the origins of that come by, but you need to be able to convert between root mean squared and the voltage associated with the DC circuit, if you will, or the voltage, the maximum voltage that is output. And then in this area right here, I ask you to pull out 3 different values. One of these is going to have a frequency below resonance frequency. That resonance frequency is that frequency that you'll capture in the body of this data as you go along, and then you'll change that to something either larger or greater in these two areas here. We talked about power, how to get the power out of this. Power can be found by taking I squared times R, or I squared times Z, which is the impedance. So you should be able to get that information from the data. And then the last
quick question.
part, go ahead.
Can you please go over like the resonance part again of part 3? I don't really understand that.
Okay. So resonance. This part right here for resonance.
Mm-hmm.
Okay. So the resonance is going to be found by first you're going to figure out the period. Let me go to the whiteboard here. So the period can be found by figuring out, you know, how long it takes to go through one cycle. In this case right here, let's just say, well, we looked at one cycle. This is time here.
I thought that one cycle was just like up, down, not up, down twice.
No, it's up and then back through the trough, and then so this is
like
one cycle. All right.
Yeah.
So that's the period. Right? So the period is how long it takes to go through that cycle. So we're kind of so in this sense, the period would be half a second. Right? The period T is half a second. But if we're trying to figure out the frequency of this is how many cycles it goes through in a second. And you can see that it goes through 1, 2 cycles in a second. So the frequency F is 2 hertz. And so you got to remember the relationship between frequency and period. There's a relationship there. I'm going to leave that one up to you guys so you can kind of pull some stuff out of your head a little bit and recall some of this. But there is a relationship here between those two. Right? And then omega can be found by looking at how many radians per second you go through in this simulation. And it's also, see there's a little bit longer version in our handout. So let's look at the other handout that we want to look at as well. Let me share my screen one more time. So at the very top here, you have a handout that just takes you to this website. You don't have to sign up or anything. And it walks you through each one of these pieces, talks about impedance, just as I did. You'll see this lagging piece here, right? You can see that this lags. In this case, I think they tell you right off from the get-go, it lags by 90 degrees. You'll be able to pick off the reactance. Remember, this is the impedance of a capacitor. This part is actually, let's see, the reactance part, yeah, is the imaginary part of this complex number. So when we talk about reactance, we're basically talking about resistance. In reactance, what we talk about, or impedance, it's a way we describe it as an opposition of current. So I just like to keep it kind of basic when we first start off here, and just kind of think of it as a resistance, right? And then you can see here, to calculate omega via the frequency, you will use omega is equal to 2 pi times F. So omega is equal to 2 pi F. And you'll see a bunch of different formulas in there where they get kind of fancy on you. But just remember that omega is just that value.
And the J represents the imaginary number, just like I would, like math.
Yes. So yeah, and so when you do the calculations, you're not gonna pick off that J. You're just gonna look at the imaginary part of that real number. For some reason, they're using J. I guess that's engineering talk. I'm just not familiar with this engineering site. So probably they decided not to use I because we use I hat so much in vector notation. We also use J, but for whatever reason, they decided to use J. So you're just going to pick off everything to the right of J in your calculation.
Wait, what do you mean pick off?
So 1 over omega C is what you're going to use in your calculation.
How about the minus?
So for our, what were we looking at here? So for our resistance, our reactance piece, it could be both positive or negative. So we might want to trying to figure out what it's asking for here. So the capacitance, so it could be positive or negative. So you're gonna need to think about which one you're gonna use given the conditions.
Mm-hmm.
Okay, it could vary. Okay.
But we shouldn't have J in our answer or our calculations.
Correct. So you're not gonna use J.
Okay, thank you.
Okay. But you might use that minus sign depending on which part you're looking for. Just remember that the resistance part, which is that let's see if I can show you that, which is this R value, that number is always going to be positive. So just remember that. And let's see. And then here's just another fancy way of writing the impedance of an inductor. So just think of omega as that 2 pi times F multiplied by the inductance.
And can that be negative?
Yes, that could be negative.
Okay. So all of the imaginary parts, like with a J in front of it, they can all be negative.
They could be positive or negative, but the resistance part is always positive.
Always positive. All right, thank you.
Yes, ma'am. Yes, sir. Okay. And remember, they use U instead of V. This is just Ohm's law as it relates to an AC circuit. And beyond this, you don't really need to know too much, other than this is what we this formula right here is what I put in my calculator, except I use sine. You could use cosine to create the graph or show the equation. Just remember, in a graphical sense, a sine and a cosine graph look the same, except they're shifted by 90 degrees. So we can use either model. I just use sine in my calculation.
So is that equation going to be used in the slab, the U of T?
This one right here,
Yeah,
is it going to be used where?
in lab 9.
I don't remember. I don't think so, because this one just basically implies that you're going to figure out the voltage at a specific time. So
Right.
no.
Oh yeah, and in the U, it's actually a voltage, right? Not potential
Correct.
energy.
Yeah,
That's kind of weird.
this is just the voltage. You know, these voltages and currents are not in phase, and generally speaking, if the voltage in an AC circuit is given by this. So yeah, engineers, physicists, everybody uses different notation. So you just have to kind of get used and adjust.
Okay, thank you.
Mm-hmm. So again, this is just the voltage at any given time, just a fancy way of writing it. I would probably just remember, see, this will just be your amplitude, your high and low. You already know what a cosine graph looks like, and this is that shift. And I would probably use radians to plug it in. I think I used radians when I did the simulation here. Or actually when I use it on my calculator, I use radians and I use degrees. But on your calculator, you might want to use that zoom trig feature because it will adjust automatically to whatever you have your calculator set to. And then you'll get a nice graph. And then you can adjust as needed. Okay, and beyond that, you shouldn't really need too much of this. This is how to find the impedance or the resistance, the total resistance of a circuit, where all these components are in series with one another, and that's identical to what we did. Even though it doesn't look like it, it's identical to what we did for resistors in series, where we just sum them up. We're not going to do anything where we have a connection in parallel. This part is slightly different, and they get into another unit that I don't really want to get into, called a Siemens. We probably don't want to get into that right now, but just know, you should know how to calculate. You definitely need to know how to calculate resistors in series and resistors in parallel. And then now what they're having you do is figure out the total impedance of a circuit, given that everything is in series. Okay.